welcome to our channel. Please like, subscribe and follow for more. Here is the property of exponent, indices and logarithm. So we have those several rules, 10 rules altogether. When it comes to rule number 8, exponent to indices doesn't have any roots into base, only logarithms. Okay, part 1 of this video will start off by looking at indices. Why I'm putting exponent or indices and logarithms together is they are inverse of each other. So therefore I'm putting them together, but as of this video, first video, we will start looking at indices. Without further ado, let's dive right in. Okay, good. So we have these 9 rules of exponent, properties of exponent to indices. Alright, we'll be looking at this one. So we have identity rule, we have product, we have quotient, division, we have exponent, negative exponent, we have zero exponent, power rule, power powers, we have equality rule, we have rational exponent, and we have Euler's base. Alright, so those are the 9 rules we'll be looking at basically. Alright, let me just do these pencils. I think it's much better. Okay, first identity rule. Let me enlarge the identity rule. Any base that raised to the power of 1, any base that raised to the power of 1, we normally don't write the powers, we just write the base, meaning that 1 is present there, but no need to show. Right, for instance, let's say if we have maybe 5 to the power of 1, we don't write 5 to the power of 1, we just write 5. Or let's say you have maybe, let's say 128. So 128 to the power of 1, which is right, 128. Okay, next let's move on to we're done with identity, let's move on to product rule. So product rule states that when multiplying with the same base, we have the same base a and a, different powers, m and n. When multiplying with the same base, we just add the powers. So look at it, we add power m and n together, we retain the common base a. So for example, let's say if we have 5 to the power 2 multiply 5 to the power 3, okay, 5 are common base, so therefore we retain the common base, which is 5, and then we add the powers, which is 2 plus 3, which is equals to 5 to the power of 5. And if you translate in a calculator, 5 to the power of 5, it would give you something around 3125, I believe. Okay, that's an example of a product rule. When multiplying with the same base, we retain the common base and we add the powers. Okay, let's move on to our third rule, quotient or division rule. When divided with the same base, here we have same base, BC, BC, they're same. We subtract the powers. So you look at it, the numerator power n minus denominator power n. So for instance, okay, let me see, we have, okay, 5, okay, rather 5 to the power of 4, sorry, let me just enlarge a little bit. So let's say 5 to the power of 4 divide 5 to the power of 3. It can be written as fraction, or it can also be written as the 5 to the power of 4 divide 5 to the power of 3. So you can see we have the common base here, 5 and 5. So we just go ahead and subtract the powers. So we retain the common base, 4 minus 3. 4 is from the numerator's power and 3 is the denominator power. Alright, so 4 minus 3 is 1. So 5 to the power of 1, no need to write 1, the identity rule. So therefore 5 is our answer. Alright, let's move down to our next rule, which is negative exponent. Okay, for negative exponent we got 1, 2, 3, and those are all the same thing. So looking at negative exponent, first let's start off with, look at it, we have a base that raised to the negative power. So when a base that raised to the negative power, to express them as positive index without negative sign, we write 1 over and then the base to the power but without the negative sign. So look at it carefully. So we write 1 over a to the power n but without the negative sign, can you see? So that negative sign is taken care of by the over sign. Or you can also write as that, 1 divide, okay, a to the power of n. Okay, just the same thing. Okay, so let's look at the example. For that case, for that method, let's say if we have, 5, and let's say if we have 5 raised to the power negative 2, okay, it's equals to, we write 1 over 5 to the power 2. You see? So it will be, when I solve, 1 on 5 squared, we know that it will be, alright, 3 into 5. Excellent. Okay, that's for that case. Okay, now so that one, we got 1 over a, base a to the negative power n. So to express that as positive index, we write a to the power n, but without negative sign, can you see? So without negative sign. That's how you write. So for instance, same example as the upper, but now we write 1 over 5 to the power negative 2, which is then equals to, express as positive index, it will be 5 to the 5 squared to the power 2. And then we know that 5 squared is 25. Okay. Alright, and next, but when fraction inside the bracket that raised to a common power and that power is negative, like here we have negative n power. Alright, so we invert the fraction sign, meaning that the denominator goes up to numerator, numerator comes down to denominator. So you look at it, b becomes the numerator and a becomes the denominator. And then when you look at the powers, the power here is negative, but once when we take the reciprocal of the, or when we invert the fraction, the powers now, the negative sign goes off. So we obtain the positive powers. So that's one of the properties as well that you need to look into. So let's say for example we have, okay, let's say if we have maybe, let's say 2 on, okay, let me see, 3 on 2, all inside the brackets raised to a common power, let's say negative 2. Alright, to express that as positive index and then solve, we take the inverse of that one, so we invert the fraction now, 2 becomes the numerator, 3 becomes the denominator, the power 2, it's negative minus 2, but now it's positive 2. Alright, so that's how you go about it. Okay, we can also, or we can further expand that one, but leave it as that. Let's move on to when it has power powers, we're gonna expand. Alright, now let's move on to 0 exponential 0 power. So for 0 power, any base, any base, it can be negative numbers, positive numbers, it can be a big number or small number. If it is raised to the power of 0, it will be always equals to 1. So for instance, let's say if we have 5 raised to the power of 0, it will be equal to 1. Or if we have, let's say if we have 108 all raised to the power of 0, it will still be equals to 1. So anyhow, it will still be equals to 1. Alright. But let's say if you have something like above, get a fraction there. If you have 3 on 2 all raised to the power 0, it will still be equals to 1. So any base that raised to the power of 0 is always equals to 1. Alright, let's move on to the next, which is power rule or power of powers. So when a base that raised to a power which all raised to another power again, so we times that base, the power, we just times the power. So look at it, common base, okay, we retain the base, we multiply the power, m multiplied by n is mn. So that's it. So for instance, if we have, let's say, 2 to the power of 2, all raised to the power of 3. So it's like power of powers 2 times 3. I will retain the base, and 2 times 3, 2 times 3, which is equals to 6. So 2 raised to the power of 6. It's 64. Okay, let's move further down to rule number 7, which is equality. Okay, the rule states if A is equals to B, then A, base A raised to the power n, and base B raised to the power n. Remember that A is equals to B, in other words, meaning there's common base in either side of the equation. Then that implies this arrow sign, okay, depicts implication, so it implies, so it's a notation form of the word implies. So if we have common A, remember that A is equals to B, so that means base A and base B, they are equal. So when we have same base at either side of the equation, then we just go ahead and equate the powers. So look at it, m equals to n, m equals to n. Okay, so let's look at an example. So let's say if we have 5 raised to the power 2n, which is equals to 5 raised to the power of 6. So now look at it, we have same base, 5, 5, same base on either side of the equation. So that implies that, alright, that implies that we equate the power. So that means 2n equals to 6. And then when we solve for n, we divide 2 on both sides. So when you divide 2 on both sides, 2 divided by 2 is 1, so it's left with n, and 2 divided by 6 is 3. So therefore n is 3. So 2 times 3 is 6, and 6, so it's equal. Okay, next we move on to rational exponent or fractional exponent of powers, fractional powers. So look at the rule here. If we have a base A that raised to a fraction of m on n, we can write that as radical or set form. The denominator n becomes the nth root, and the numerator becomes the power of the base. So you follow? Look at, study it carefully. So the denominator becomes the nth root, and the numerator becomes the power of the base. Okay, so for instance, let's say, now we got further notes of that one, maybe do one in another video. So for now, let's say, for instance, if we have, let's say if we have, okay, a to the power of half, a to the power of half, which is equals to, we know that the denominator is the nth root, so nth root is 2, and then we have a, and to the power of 1, no need to write 1. So for square root, we don't write a second root there, we just put the root sign. So you can see here, root of a. So any base raised to the half power, that means it's a square root. Any base that raised to the 1/3 is a cube root, and any base raised to the 1/4 is a fourth root, fifth root, and so forth. Okay, so let's look at an example. Let's say we have a base A, okay, raised to the power, okay, 3 on 5. So if you raise to the power 3 on 5, express that as radical or set form, the denominator becomes the nth root, remember that. So therefore it's fifth root of A raised to the power 3. So that's how you write and you express that. I'll do another video of that one, going through the notes. And then the last but not the least, that ninth rule, it's realized based. Most of us, you'd come across this E key on your calculator, scientific calculator, and you might know under. So if you punch that one, E and equals, you'd have, it will give you that number. Let's say, okay, 2.718281828, and the number goes on. And it's a irrational number, meaning that does not have a recurring decimal. So that's all for today. Please stay tuned and follow for more.